For decades, society has treated digital innovations as isolated tools. You have an application on your phone, a program on your laptop, and data centers processing requests through brute force computing power. We have scaled our technology by simply plugging in more machines. This line graph maps global AI energy demand against our physical infrastructure. The trajectory of modern computing power is crashing into the limit of our current electricity grid. Generative AI requires so much energy that we are mathematically running out of power to run it. The tech industry cannot solve this by simply building a faster, isolated tool. The physical limits of our hardware are forcing a complete redesign. We have to construct an entirely new, interconnected planetary-scale infrastructure. Right now, 9 distinct technological frontiers, spanning robotics, quantum computing, bioengineering, and nuclear energy, are colliding. They no longer develop in silos. They're actively forcing a global transition. This marks a shift in our relationship with technology. We are moving from the era of using tools toward an environment where autonomous systems plan and execute the tasks that keep the world running. It begins with Agentic AI. This is a leap past models that simply generate text or images. Agentic AI is software that autonomously plans and executes complex, multi-step workflows. It interacts with other programs and adapts to new information without human intervention. To manipulate the real world, this autonomous software requires a physical vessel. This requirement triggers the mass deployment of humanoid and autonomous robotics. Systems like the one you see here are moving out of laboratories and directly into logistics centers, factories, and domestic spaces. But powering millions of these continuous learning physical AI agents requires an impossible volume of traditional electricity. If we attempt to scale these robots globally on our current architecture, the grid will fail. This comparative visualization shows the difference between traditional computing and neuromorphic hardware. On the left, traditional architecture processes data sequentially, burning massive amounts of energy. On the right, neuromorphic chips mimic the neural structure of the human brain, firing in parallel spikes. This biological approach processes information in real time while consuming a fraction of the power. Even with highly efficient chips, the macro-scale grid requires an overhaul. To provide the massive zero-carbon baseline power the AI ecosystem needs, the industry is accelerating advanced nuclear technologies. We are deploying small modular reactors and racing toward commercial fusion to meet this intense demand. The evolution of AI software has directly triggered the forced reinvention of our physical infrastructure. Intelligence cannot scale unless the power grid scales with it. To process the extreme complexity of this new world, we turn to quantum capabilities. Quantum computers, like this system at Google, bypass classical limits entirely. They use the principles of quantum mechanics to instantly simulate complex chemistry and molecular physics that would take a traditional computer millions of years to calculate. That simulation power hypercharges bioengineering. By perfectly modeling molecular interactions, scientists can design personalized CRISPR therapeutics, engineer living medicines that adapt to your body, and even 3D print viable organs. All of these individual leaps, robotics, bioengineering, and quantum systems, must communicate instantly. Advanced connectivity, driven by emerging 6G networks and thousands of low Earth orbit satellites, acts as the mandatory connective tissue, linking these distinct technologies into a ubiquitous global nervous system. Humanity's interface with this network will bypass traditional screens. Immersive reality and spatial computing blend digital information directly into our physical environment, allowing us to interact with this vast ecosystem intuitively. However, this immense connectivity creates a catastrophic vulnerability. A capable quantum computer can easily break the cryptography securing the modern internet, while AI agents can automatically probe networks for weaknesses and execute sophisticated hacks at scale. Because of this, digital trust and post-quantum cryptography have to become the foundational layer of the ecosystem. We are deploying new cryptographic standards and zero-trust architectures to defend against these exponential threats. In a system this integrated, a cybersecurity failure can cascade across power grids, hospitals, and logistics networks. A breach here targets the physical infrastructure we rely on for survival, shifting the risk from digital records to human safety. These 9 technologies are fusing into a single global operating system. We're seeing a transition where physical infrastructure and digital logic function as a single, unified machine. Controlling this operating system is now the focus of the most intense economic and strategic competition in human history. The United States currently holds a commanding lead in raw AI innovation and model development. China, however, is heavily leveraging its capacity to mass manufacture and scale the physical vessels. They are already installing more than half of the world's new industrial robots and rapidly advancing humanoid platforms like these. Meanwhile, the European Union is establishing a distinctly different strategy. By focusing on comprehensive regulations and compliance, the EU aims to act as the world's primary ethical counterbalance, attempting to rein in the risks of these interconnected systems. The ultimate advantage belongs to the nation that successfully scales and integrates all 9 of these frontiers simultaneously. This race is won by the strength of the entire converged system, from raw AI innovation to the manufacturing of energy grids. We are actively assembling the architecture of the next century. Managing it requires an urgent and precise balance between unlocking human productivity and navigating systemic existential risk.